All right, ladies and gentlemen, this is going to be review video number 16 that's going to cover types of solids. There are 4 main types of solids that we're going to discuss. 2 of them you have already heard of, and 2 of them will be new to you. So, ionic solids comes first, and ionic solids can form when a bunch of cations and anions, or our positive and negative ions start stacking up and stacking up and stacking up, just like you're seeing over here, into a crystal lattice structure. And those are going to be held together by something called electrostatic attraction. An electrostatic attraction is just a very fancy term for an ionic bond. Ionic solids tend to have some common properties. They tend to be brittle or hard. And the reason they tend to be both brittle and hard is because there is an element of repulsion that can happen when we start stacking ions next to one another. But basically, when you apply a force specifically this way, what happens is all of your ions shift as a result of that force. So everything's moving to the right. So this one moves out of alignment. That one becomes positive. That's negative, positive, negative, positive. And so now what we're seeing is we're seeing a repulsive force between like charges that causes that ionic crystal lattice to shatter rather than bending like a metallic substance would. Ionic substances also are going to have really high melting points. And the reason that they have really high melting points is because every single ion in this lattice structure is held together through ionic bonding. And ionic bonding is a true chemical bond, and as such, it requires a ton of energy to break. And if you require a ton of energy to break, that means that you have a high temperature requirement to melt. Ionic compounds are going to be poor conductors in solid state, and we've already talked about the reason why, but as you know, due to that alternation of charge, when something bonds together ionically, the ionic bond itself is the attraction between those oppositely charged ions. But what happened right before that is that our cation had transferred its electrons over to the anion, which has a really strong pull on them. And so those electrons cannot move around. They're just going to circulate the anion and be locked in that spot within the crystal lattice structure. So since those electrons cannot move around, we are a poor conductor in solid state. But if you melt that substance or dissolve it in water and suddenly those ions move apart from one another, any resulting electrons are now free to move around as the ions themselves move around. And so we get more conductance in liquid or aqueous states than we ever would in a solid state with an ionic substance. The big takeaway for this is that our ions are held together in an ionic substance by specifically ionic bonds. All right. Next type of substance I want to talk about is a molecular covalent solid, right? So this one is a little bit of a new thing for you. So a molecular covalent solid is formed when adjacent covalent molecules are attracted to one another through specifically IMFs. And we learned recently what IMFs are. Those are intermolecular forces, or forces that occur between adjacent molecules. So all these little iodines over here, this iodine and the iodine next to it, would be attracted to one another through intermolecular forces, specifically London dispersion forces. Same with this carbon dioxide. That's going to be attracted to another carbon dioxide around it through London dispersion forces, because carbon dioxide is a nonpolar molecule, as is iodine. All right. Any substance that is a molecular covalent substance is either soft as a substance or it's brittle, right? So let's talk about a soft version of that. Butter would be an example of a soft molecular covalent substance. Because even when butter is solid, it's really soft. You can depress it with your fingers, so on and so forth. But if we're talking about solid carbon dioxide or dry ice, we know that that's a little bit more crystalline in nature and it's a little bit more brittle. Those substances are going to have low to moderate melting points. And the reason that they do not have high melting points is because intermolecular forces, IMFs, are easier to break than a true bond is. So an ionic substance that has ions that are ionically bonded to everything else around it, that takes a lot more energy to rip apart than a covalent substance where you only have to break the intermolecular forces between different molecules. All right, covalent substances are always going to be poor conductors because they do not have metals. So it doesn't matter what state they are in, solid, liquid, gas, doesn't matter. They're not going to conduct electricity. In a molecular covalent substance, those molecules are going to be held together through intermolecular forces, either London dispersion forces or dipole-dipole forces, or through hydrogen bonding. Any of those could hold a molecular covalent substance together, but it does have to be an intermolecular force, not ionic bonding and not covalent bonding. Next type of substance, again, new to you, is a network covalent solid. So, a network covalent solid is honestly the most similar to an ionic solid than a molecular covalent solid, because what a network covalent solid is another like lattice structure, but instead of every atom being joined by ionic bonds, those atoms are actually joined by covalent bonds. So we can see a couple of examples here. So we see a covalent bond here, we see a covalent bond here, covalent bond, covalent bond, covalent bond, covalent bond. So just like in an ionic structure, all of those carbon atoms, are going to be joined together by a true bond. It's just a covalent bond rather than an ionic bond. So this represents diamond's structure. Diamonds are made entirely of carbon, specifically sp3 hybridized carbons. And then this on the right here represents graphite, which is also made entirely of carbon, but those carbons are bonded together a little differently. Each of these carbons are sp2 hybridized instead. And so we're seeing two completely different looking lattice structures, and therefore we have two completely different sets of properties. All right? Any network covalent substance is going to be very hard and very strong. Why is that so? Because covalent bonds are the strongest type of bonds. And so especially when you're looking at a substance like diamond, where every single carbon atom is connected to every single other carbon atom by a covalent bond, that means that it's going to take a lot of force, a lot of energy to break those associations. And similarly, graphite is going to be pretty strong as well. But the interesting thing about graphite is that graphite tends to form layers, and we're seeing those layers on the right-hand side there. And so graphite is a little bit less hard and a little bit less strong than diamonds, so much so that you can write with it, because graphite is actually what your pencil lead is. It's not lead at all. It's actually carbon atoms structured together like graphite, because those layers can slide off of one another. Our network covalent substances are going to have very, very high melting points. And again, the reasoning for that is because of your covalent bonding. Covalent bonded substances that network like this have higher melting points than any ionic substance. So diamond's melting point is crazy, crazy high. Generally speaking, our network covalent substances are poor conductors. Not always. There are certain exceptions to that rule. You don't really have to know any of them offhand, but you do have to be able to evaluate whether or not a substance might or might not be a good or bad conductor in certain circumstances. So to explore that, let's go back to graphite here versus diamond, right? Graphite and diamond are both made entirely of carbon. However, whereas diamond's structure does not allow for any atom movement, graphite's does. And carbon is a little bit special in that that movement can allow for a little bit of electrical conductivity. So graphite is a bit electrically conductive, whereas diamonds are not. Now, 3 examples of network covalence to know. We've talked about 2 of them already. Diamonds, graphite, and the last is silicon dioxide. Silicon dioxide is your main component of sand, and it's interesting because silicon is a metalloid, but yet it bonds covalently with oxygen and it forms this lattice over here, which is a network covalent lattice. Our main takeaway of this is all atoms in a network covalent substance are held together by, shockingly, covalent bonds. I've said it a bunch of times already. Last type of solid that we want to worry about are metallic solids. As their name suggests, they are made up all of metal atoms, though there are a couple of instances of metallic solids that are interstitial in nature, where little non-metals can kind of nestle their way in between those metal atoms. Metals, there's a giant range for. They can either be soft metals like sodium and all the stuff on the left-hand side of the periodic table, or they can be really, really hard and really tough like iron or zinc or any of the stuff in the middle of the periodic table. As such, they also have a giant range of melting points, with a couple of metals actually existing in liquid state at room temperature, like mercury or gallium has a melting point just above room temperature, versus things like iron or zinc or silver. You have to pump them full of heat before they have any chance of melting. They are highly conductive because their electrons can move, so that's what electron motility means. And due to that electron motility, they are also malleable and ductile, meaning that if you apply a force, those metal atoms are just going to bend around one another rather than shattering as ionic crystal lattices tend to do. And our atoms in any metallic substance are going to be held together through metallic bonding, otherwise known as that electron C that we've seen a few times now. Couple of important terms to know about solids. There are two main types of solids that we can group each of the four that I've already talked about into. So the first is called an amorphous solid. And an amorphous solid is a solid that exists, but it lacks an ordered structure. So a couple of examples of amorphous solids that you've heard of would be glass, plastic, or rubber. And they're going to have just like kind of a random looking structure if you look at it on a chemical level. So we can see that there's no pattern to this. The atoms are just kind of wherever they want to be. Glass, on the other hand, over here has slightly a better order about it, but still, like, it's not pretty, it's not crystalline in nature. The atoms are kind of just squeezing in wherever. Typically, because of their randomized structure, amorphous solids tend to soften over a range of temperatures rather than having a distinct melting point. So the thing that I want to cite for that, once again, would be like butter, right? Because we know that butter, it has a melting point really, really close to room temperature, right? If you hold it in your hand, it's going to melt. But if you put butter in the microwave and you start heating it, it's not as if it's solid, 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 and then it melts all at once. It softens over time. And quite often, if you put butter in the microwave, you have to microwave it a few times to get all of that butter melted. And so that's what I mean by these types of solids tend to soften over time rather than having a clean melting point. All right, crystalline solids is the one that you're more familiar with, and those are solids that do in fact have an ordered structure. So quartz is an example of a crystalline solid, silicon dioxide, diamonds, any ionic compound that we've looked at so far would be a crystalline solid, and it's just distinct because it has a very ordered shape and structure. If you have any issues understanding any of this, please let me know.